All right, welcome everybody. Today we're going to talk about our confidence interval estimates for population proportions, going through those calculations, how we go through that work, and some of the information there. So let me start to share my other camera so we can see the document camera, and we'll go there. All right, so now looking here, we have some problems to do later, but in our work with our confidence interval work, right? Confidence intervals for short, but our confidence interval estimates for these population parameters. So getting a chance to practice with some of our vocabulary, the language we use as well in some of that terminology, right? And so in this case, the major idea is that we're going to use some sample data, whether it be from a raw set of data or from values that have been computed using sample data. We're going to use sample data to, as it says, kind of estimate these values or results, those parameters we'll talk about, right, for a population. Right, because again, calculating a precise value for a population, the mean, the proportion of the population that has a particular characteristic or standard deviation, right? Even more difficult, right? Trying to get those values for a full population, getting all that data would be difficult. And so more realistic that we use a sample to try to estimate, to identify what's going on for that population. Okay. And so just for some terminology, remember here that a parameter, right? This is a value that result computed, right? Using that full or entire population set of data. Right. And so with those parameters that we've been working on, we started talking about in chapter 3, right? In our numerical summaries, so on, right? We had for our mean, that population mean, we use this Greek symbol mu. For proportion, here we just use P, or I'll also probably use a capital P, but P. And then standard deviation. If we have the standard deviation for the population, that unadjusted standard deviation we've talked about before, right? That was that symbol sigma, those Greek letters, right? And so then here for our sample information, that's when we start talking about having a statistic, right? So a statistic, this is a value computed using a sample of data, right? Having that sample taken from our population, of course, but the important aspect here, sample, and again, associating sample with statistic, those two start with S. For population, we get a parameter, okay? And so the idea that, well, definitely it's going to be much more difficult to get the full population set of data. So we start with some sample, right? Taking a sample of 50 students and using their data to figure out, okay, what's their average number of hours they work per week, or the average they spend for groceries, or whatever it might be, right? And so in this case, that average or that mean, when we're talking about for a sample, X bar. When we're talking about a proportion for a sample, that's when we had P hat, right? How many people out of this sample have a particular characteristic. And then for standard deviation, we use that symbol S, right? And remember, for our variances, the variances are the standard deviation squared. So the population variance would be sigma squared. The sample variance would be that sample standard deviation S squared, so on. Okay. And so the idea is that, well, if we can't calculate for the full population, we don't have access to all that data. Hopefully we can get a good estimate. We can kind of get a guess of what that population value would be based on that sample data. Okay. And so using that information, as we start to build up those estimates, right? What we're going to do, we're going to start to, right? We create confidence intervals, right? This range of values, okay, right? To estimate this range of values that population parameter, that value for the mean mu, that value for the proportion p. We could also talk about standard deviation, okay, that's sigma, but we get this range of values that the population parameter could fall between, right? Could be equal to some value in between those values. And so kind of our general setup here is that we have our parameter, that value for mu, for proportion, standard deviation, so on. And we're going to set up this range of values that it can be above, greater than this quantity, or lower than this bound, right? And so we start to see kind of like these lower bound, that lower value that it might be equal to or above, and we have that upper bound, that upper end of our interval, okay? And we start to make those estimates, okay? And so then here we know we can't be perfect, so that's when we start to build up this idea of having a confidence level, okay? And so here, we know our estimate could be wrong, right? That interval, that range of values that we have might not actually include, right? Our interval may not include, it might not encapsulate, incorporate that actual population parameter. Maybe our estimate is too high or too low. So in our work, right, kind of we assign a confidence level to our result, right? Or we incorporate this confidence level in the production, in the creation of that interval, okay? And so here, as we start to look at that, right, we have our confidence level. Sometimes in my notes, I'll kind of shorten that to be CL, okay? And our most common confidence levels that we see, right? 90%, 95%, 99%, right? Basically, we're going to be 99% sure, right? Confident that in this interval that we create, that range of values, we're 99% sure, confident that our parameter is in between those values, right? Or 90% sure, right? And really, it can be any percentage, but these are the three most common that we're going to see. But it could be 98%, 97%, 83%, whatever you like, okay? But again, those are the most common. And so one way we kind of phrase it, right, is kind of easily discussing is like how confident we are, how sure we are. But truthfully, these confidence level, right, is kind of, we go through this process of calculating based on different samples, right? We just take one sample, 50 students, maybe another group will take another sample, and their estimate might be different, right? So we can look at all those different possible confidence intervals that we can create based on all those different samples. And these confidence levels are saying, okay, that if we had the opportunity to take all those different samples, right? That 99% are going to hold that population parameter. There's going to be that 1% that could be wrong, right? Or 90% of all those different possible results we could have had, all those different samples we could have tried to build that interval. 90% of them are going to have the actual parameter there, but there's going to be the leftover 10% that are not going to include, that are going to be wrong, if you will, that don't include that population parameter. And so now, in that case, this value for alpha is 1 minus our confidence level, 1 minus that 90% or the decimal 0.90, 1 minus 95%, 1 minus 0.95, right? That 5%, 10%, this alpha, right? And what this alpha represents for us, this is the probability, the chance of making an error. This type 1 error discussion, right? The probability of making an error, the probability, right, that our confidence interval is wrong, that it doesn't include that population parameter, okay? And so where we're going to see this alpha, this probability of making an error, okay, as we start to build up these formulas and start to see those, we'll do this on StatCrunch as well, right? That we use that value for alpha, that probability of making an error, there's our symbol, just kind of give that word to it as well, right? As the area, I'll say split between the tails of the distribution used. We saw our normal distribution, that bell-shaped curve, our z-scores, right? We saw that before in chapter 7, a normal distribution, right? Even with our sampling distribution that came up. And we're going to see it again in some of the calculations. We'll also introduce a new distribution as well, okay? And so in this case, making this note, right? For estimates, these confidence intervals and later tests for proportion, right? That parameter P, we use that normal distribution. Those kind of z-scores, those z values that we saw similar chapter 7, okay? And so in that work, we kind of build up our normal distribution curve. We have those z-scores along that bottom axis. We know that the peak, the middle of that bell-shaped curve, is at that z0, our standard deviation 1, mean 0, right? That work. But now, kind of getting into that discussion with our alpha, that probability of making an error, we're going to see that this area in these two tails is going to be alpha over 2. Alpha over 2 for that area. And so then what we're going to start to look for in terms of our calculations, we need these critical values, these cutoff values. And it's going to be the negative on this side, positive on this side. Again, here we might call it CV for short, but that's that Z sub alpha over 2, right? Because it's that Z score corresponding to having an area of alpha over 2 in that tail. And by symmetry of the normal distribution, we'll get a positive value for the right and make a negative, right? That's a negative value for the left tail, okay? And we can find that using our normal distribution, but likewise in some of our calculations, it'll show up in StatCrunch there, okay? And so in that case, when we start to work on those, we can find those cutoff values, okay? I'll make a note for this case, right? For estimates for the mean, this value mu, okay? We kind of have two cases, very rare. If we know, if we have that population standard deviation, and usually that's presented like, okay, from a previous study, we know this value. But truthfully, how can we know the population standard deviation sigma if we don't know the mean already? But if we know that population standard deviation, we use the normal distribution, those z-scores again. And so in terms of our cutoff value, very similar to up here, right? We're going to see those z sub alpha over 2, just like proportion. But much more common, a little star next to this one, this is more common, right? If we only have the sample standard deviation, and that's much more common, especially if we start to do work in the real world where you're working with a sample and you have their sample standard deviation for your project. We don't have access to the population standard deviation, right? We use what they call the student t distribution. And I'll probably shorten it a lot of times in our work and just call it this t distribution. We're going to start to see these values t sub alpha over 2. And that t distribution looks very similar to our normal distribution, that t axis down below now. But it looks a lot like our bell-shaped curve. My normal distribution, I'm going to make it a little bit higher, a little bit wider. Okay, we still have that aspect of having 0 in the middle, that symmetry. I know it's kind of expanded, but we still have this area alpha over 2 we can identify. We're looking for those cutoff values, those critical values, like so. Okay, but now with our t distribution, we have to worry about a degree or these degrees of freedom, df for short, which depends on our sample size. Is this n minus 1? So depending on how big of a sample we have, right? We have 30 students that we've surveyed, right? We have 15 voters in the city that we're going to survey, that we're going to question, right? Measure, whatever it is. And this shape, right? Kind of how wide this is, the bigger the sample size, the bigger the value for n, the closer this looks like the normal distribution, because slowly but surely we're building up to having that full population. But when we start with samples, it kind of gets a little bit wider, but it shares those same characteristics, right? So we have these kind of cutoff values, these critical values corresponding to this area alpha over 2 in the tails, where again, that alpha represents that probability that we're going to make an error. Where that shows up is that, okay, we can take all these different samples, and there's a chance when we start to build up to figure out where a population mean will be, that our sample value is kind of, in the mix of our common results. And so when we make an estimate based on that sample, we're likely to get an interval that includes the population mean. But there's the chances that maybe that one sample I get is really large compared to the rest. And when I make that interval, that range of values around it, it's not going to include that mean, right? So that's where that alpha shows up, how these area the tails, because there's a chance we get a value that are too far away so that our estimate isn't going to be accurate, okay? And so going through, we'll look at those critical values, those cutoff values, and we'll talk about for our formulas then, where they show up. But truthfully, with StatCrunch, we don't need the formulas, but talking about these, our formulas for confidence intervals. We have, of course, for proportion, when we're estimating the population proportion, or sometimes the book will call it the true population proportion, the true proportion, right? We have our value for P. That's the value we're trying to figure out what this could be between. And so when we start off with our sample value, right? If we're trying to make a guess, well, we can take our sample proportion, that P hat, X over N, right? How many people, how many values in our sample have a particular characteristic. We start off with that same point estimate, our sample value, and then we're going to either add or subtract a little bit of error, right? We're going to give ourselves a little bit of wiggle room there. And so with proportion, that amount of error, right? Like we mentioned before, we're going to use that critical value, that cutoff value, that Z sub alpha over 2. So there's our critical value based on our confidence level, based on that probability of making an error. That area we're split into the two-tailed, alpha over 2, based on that critical value. We'll get here, and then we're going to multiply this by the square root. And again, with our sampling distribution, you might remember how we computed that standard deviation we would use. Okay, but now that we only have sample data, we're going to take our sample proportion, P hat, and multiply it by 1 minus that P hat, right? Those complements. And we divide that by our sample size N. So in green there, that's all that sample data. Critical value Z sub alpha over 2 from the normal distribution, that cutoff value. Okay, and then again, is going to mimic the same calculation on this side. Inside that square root, P hat, our sample proportion, times 1 minus that sample proportion, all over N sample size. And so now we have our point estimate, that P hat, okay? Our initial guess, if I had a single value to guess what that population was, I would just use my sample, right? My sample proportion. And that P hat, we can calculate by X over N. How many have our characteristic out of the sample size, okay? Sometimes we use it as a percentage. You always write these as a decimal, right? And then this amount that we're adding, subtracting, right? There's the same point estimate, right? That's Z sub alpha over 2 times that square root, P hat times 1 minus P hat over N inside that square root, right? That amount, this is our margin of error, right? How much error we're going to allow. We know we're not going to be perfect in our estimate. So there's a little margin of error, right? That standard error here, that quantity, okay? And so we can use that formula, but truthfully, in our work, we'll see StatCrunch being used a great deal, right? So then when we start to deal with the mean, this estimate for mu, following a similar pattern, right? We have those two options. And so in this first option, right, if we know sigma, the population standard deviation, then our formula, right, we're going to take that value for mu we're trying to estimate, and we're going to put it between, right, lower bound, upper bound, our sample value, our point estimate, X bar. And now we're going to add or subtract our amount of error, this margin of error. And in this case, for our error, when we know this population standard deviation, again, pretty rare, we'll see Z sub alpha over 2, that critical value. But now for our margin of error, we're going to multiply that by our sample standard deviation, over the square root of n. Or not sample, population standard deviation, sorry, that population standard deviation over the square root of n. There we go, better. Right, since we know the population standard deviation, we should use those over the square root of n. There we go. Again, very rare that we have that population standard deviation, but something we can consider. Much more common, right? If we only have that sample standard deviation, then in our estimate for that population mean mu, once more, we're going to start off with that x bar, that sample mean. We're going to add, subtract. But now, if we only have that sample standard deviation, now we're going to use the t distribution, t sub alpha over 2 here. And now this is where we're going to multiply by s, your sample standard deviation over the square root of n. S over the square root of n. That's standard error, okay? And again, nearly identical. We just have to pay attention to which distribution we're using. The z distribution, t distribution, when we're dealing with that mean. Okay, there's a whole new distribution for the standard deviation, but we'll deal with that at a different time. Okay, so now with all that set up, right, there's our formulas we can talk about. Let's go into some problems here where we can start to compute, build up these intervals for our confidence interval estimates of these population proportions. Okay, all right, so now starting off, I'm going to start off with proportions. Okay, doing these confidence interval estimates for the population proportion, right? And so we're going to start off with this survey of data. Let me get this a little bit closer. And then I'll also bring up StatCrunch in a moment for us to view, okay? But in the problem, right, in a survey of 104 California residents, 42 felt that the governor has not focused enough legislation on education, right? So a lot of times we'll see these kind of estimates used in politics, right? In these voting, how people are choosing to vote, so on, whether they agree or disagree with some action. So now the first part, we're going to find a 95% confidence interval for the true population proportion, right? That P of Californians that feel the governor has not focused enough on education, right? To have this characteristic. And so as we start to read through, okay, so we've surveyed 104 California residents, right? So in this case, put it here in red, right? There's our value for n. We know there's a lot more than just 104 Californians that are going to vote, so on, but just California residents in general, a lot more than 104. So this is definitely just a sample. And of those, it said that 42 felt that the governor has not focused enough legislation on education, right? So in this case, these 42 that had this characteristic, there's our x. X is equal to 42. Okay? So out of those 104, 42 felt that the governor has not focused enough legislation on education. And so now as we go forward, we want to, in part A here, find, or sometimes they'll say build or create a 95% confidence interval. So there's our confidence level, 95%. But when we work in our calculations, we always go into decimals, so 0.95, for the true population proportion. Population proportion, so we want to get that value for P, right? So now in this problem, right, our goal, our hope here is to have this interval where we have our proportion P in the middle for our population. And now we need to figure out what that lower bound and upper bound values are going to be, right? What that population proportion might be with 95% confidence based on this sample of data, okay? And so looking at our formula, just so we have that there, right? Our formula, P hat minus that Z sub alpha over 2 times this big square root, fraction aside, P hat times 1 minus that P hat, that sample proportion, all over n, kind of getting those color coordinate. So there's our lower bound, our point estimate, our sample proportion P hat minus that error. For our upper bound, let me put my population portion P in the middle. That same set of calculations, but now we're going to swap that subtraction with an addition, right? Get a little bit above that point estimate. Make my square root symbol 1 minus my placeholders, I call them. I'm filling right P hat times 1 minus that P hat, that sample portion, all over N. Okay. And we'll do this on StatCrunch as well. But as I start to set this up, okay, off to the side here, our value for P hat is going to be X over N. And so in our work, we're getting 42 over 104. I'm going to start to share my calculations on our other screen here. And then I'll share my StatCrunch window. There we go. All right. So we should see my StatCrunch window. There we are. Okay. Sharing. Sorry about that, folks. Okay, and then likewise, let me, so you're not looking at my face here, but you can see the paper. Let me switch this one. There we go. Okay, so now we should see both the paper as well as our StatCrunch screen here. But initially, as I was writing, right, we can first calculate that P hat. Here's my Desmo scientific calculator. We'll do the formula work as well. My apologies, my unit's a little bit slow. There we go. Desmos. Here we go. So now looking here, we want to calculate our sample proportion. This will 42 over 104, right? We're going to get this long decimal, okay? And we'll see how this shows up in StatCrunch as well. But for that P hat, the long decimal, 0.4038461538. And typically when it comes to proportion, we're going to round to 3 decimal places, right? So when it comes to showing our work, right? Showing this long decimal result, then we round to 3 decimal places. That 8 is going to round that 3 up. So from our P hat, as we can see here, 0.404. Okay. All right. And so then in terms of our confidence level, we saw that was 95% or 0.095. So for our value for alpha, 1 minus our confidence level, 1 minus that 0.95, our alpha 0.05, right? 100% minus 95%, 5%, 0.05. And we want to divide that by 2. So 0.05 divided by 2, our alpha over 2, 0.025. That's our area in that tail of our normal distribution. So when I go to look for that z sub alpha over 2, if we look at our StatCrunch work, getting that critical value, stat, calculators, normal distribution, normal calculator right here, right? So kind of what we did for chapter 7, chapter 8 work. Now, if we know that the area in that left tail, we're talking about z-scores, so we're going to leave the mean as 1, standard deviation, or mean is 0, pardon me, standard deviation 1. But now, if I don't know that cutoff value, but I know my area in that tail is 0.025, there's this quantity, negative on the left side, right? If we do greater than, and let me close this, and I do 0.025, we have the same amount of area in the right tail for the greater than. We get that positive now, right? That 1.95. So with all that work, with our normal calculator, we see that cutoff value. We're going to round it to 2 decimal places, which come with our z-scores, is 1.96. Okay? When I take that long decimal, round it to 2 decimal places, that 5 rounds up because of this 9 Okay. And so when we go into our formula, we can write that all out. But while we have StatCrunch here, we could move this over. Okay. We can do these calculations for the confidence interval right away. So now in StatCrunch, now we're going to do proportion stats. So looking under that stat menu, proportion stats, we only have one sample that we're working on. In the future, we can talk about comparing two different samples, but we have one sample and we have this summary, right? We have how many values in our sample have that value. We don't have the raw data. We don't have that list of 104 people. We just have that summary for one sample with summary. And so now here are number of successes, that's X. In this case, we have 42 successes, observations, 104, right? That's how many California residents. We'll talk about doing a hypothesis test in the future. Right now, we're doing a confidence interval, so I highlight that dot. Confidence level, 95%, 0.95, notice again is a decimal. Just leave the standard method here to kind of mimic what we saw with our normal distribution. We'll say show the critical value. I'm not going to worry about the graph. I'm not going to store the data in a table. Showing the critical value, standard, confidence level 0.95, X, the number of successes, and the number of observations, computing. And there's our value, right? So our sample proportion, just like we had calculated on Desmos, right? That error, that Z times the square root, our critical value, our critical Z score, same thing we got right here, notice it. And so now we have our lower limit, upper limit. So here I call it a bound, they call it limits, that's fine. So from StatCrunch, right, with those value, X is the number of successes and the number of observations. So from StatCrunch, right, using that stat menu, then we did proportion stats, I believe it was called, right? Then we did one sample with summary, right? So kind of highlighting those components. Now, for our proportion P, that for the population, we're estimating with 95% confidence that our lower limit 0.3095 4466 for the lower limit or lower bound, I call it up here, same idea. Upper limit, upper bound, 0.498 14765, right? Your upper limit. And so when it comes to proportion, we're going to round to 3 decimal places. So in that case, this is going to be 0.3. That 5 rounds 9 up. Well, I can't put a 10 there. So slide over that 309, 309 becomes 310310, right? Less than our population proportion. Less than. And now when I round this upper limit, upper bound, the 3 decimal places, 0.4. This 1 keeps the 8 the same, so it's going to be 0.499. So we can write it like so, right? That we're 95% confident that our population, if I was able to take all California residents and measure the proportion that feel the governor has not focused enough the legislation on the education, that with 95% confidence, it would be between 0.310 to 0.499, right? So we're kind of saying that between 31.0% to 49.9%, almost 50%, right? With 95% confidence, feel that the governor has not focused enough legislation on education, right? And so very briefly, just looking at that lower limit, let's say, if we go to our Desmos calculator and we're to calculate, if I do the rounded values, right, for my p hat 0.404 minus That z-score, 1.96. The negative is taken care of me already. So I just put the numerical value at 1.96 times the square root, and we make a fraction inside, right? That's saying 0.404 times, now parentheses, 1 minus that 0.404. There's our p hat times 1 minus p hat all over n. Our sample size was 104. Right, a little bit different based on our rounded value. We didn't keep that long decimal for p hat. You could just copy and paste. And even with that critical value, that z-score, it's a little bit different. But with rounding, with our values here, that's that same lower bound we just found, right? That 6 is round the 9 up. So we get that same lower bound, lower limit with rounding that we had here, right? This is going to be a little bit different because of the value. They use those full decimals for the sample portion, that full decimal for the critical z-score, that z-score over 2 in the formula. But when it comes to our work showing those long unrounded values, then your rounded results, we can follow along. Okay. All right. So then looking at the next problem from that sheet, using that same data, but now what happens if we want to create, if we want to build up a 99% confidence interval, right? So now in this case, if our confidence level is 99%, right, 0.99 as a decimal, our value for alpha, 1 minus that 0.99, 0.01, that 1%, and if I do alpha over 2, 0.01 divided by 2, we're getting 0.005. So now we have a much smaller error. Our area, we're hoping for less likely of making an error in our calculation. And now if we do that work on StatCrunch again, I can close that down. We can close this one down. We can compare, but in proportion stats, one sample with summary, same number of successes at 42, observations 104, again, same sample, but now we're going to change the confidence level to 0.99, 99%, showing our critical value, computing here. So now our critical z-score, 2.5758293. What we'll kind of commonly see is that z cutoff value with 99% confidence, 2 decimal places, 2.58. Okay, that 5 here rounds the 7 up, so we go 2.58 commonly. So we can do that in our formula like we did a moment ago. But now our lower limit in that buildup, right? So using StatCrunch again, same set of steps, our population proportion is going to be between. And now for that lower limit, I'll put in red, 0.27991298. Upper bound, 0.527777932. A lot of sevens there. Rounding to 3 decimal places. This lower bound, we're going to, that 9 rounds that 79 up, 0.280, less than our population portion. Rounding this to 3 decimal places as well, 0.528 this time. Right, and again, if we do it as a percent, 28.0% for my lower bound, that lower limit, up to possibly 52.8%, right? And so with 99%, I'm going to be more sure that we're going to incorporate, we're going to include the possibility of having our population proportion in our interval estimate. With 99% confidence, we consider that the proportion from the population that feel the governor has not focused enough legislation on education is between 28.0% up to 52.8%, right? That decimal 0.280 to 0.528, right? So a lot of times I'll ask for the decimal form, but we can translate into percentages just the same, right? And we can use the formula, watch out for those calculations, right? That StatCrunch, whether you use that normal calculator and think about how much area is in that tail, or on StatCrunch with those proportion stats, show the critical value, and it'll give your critical value, that cutoff score, just as we would with a normal distribution. Okay. So then, as we go into that work for the mean, right, we'll see very similar actions that we did with our proportion. So now, with this one, let me close this down. Okay. If we have on our sheet here, okay, let me share this a little bit differently. Let's see if this is better to view, like so. We'll do that here. All right. Okay. There we go. Let's see if this is nicer. Okay. So in this case, if we have on my screen here, now let's see. Let me try one more time. Sorry, folks. Do this, that. Go. And then the other one will be that's okay. Let's try this. Okay. So now we should have both of these here. Okay. So now we can see that handout, sheet of practice. So now we're going to estimate that population mean, right? So now we're going to build up that interval for the population mean mu. So now starting off, the city planner wants to estimate the average monthly, right? Average, the same thing as the mean monthly residential water usage in a city, right? So they're trying to build up that population mean mu. The city planner selected a random sample of 40 households, right? So sample of 40 households. So there's our N off to the side here. Sample size of 40, which gave the mean, right? So from that sample of 40, gave the mean water usage of 9,415.7 gallons. So there's our X bar, right? From that sample of 40, they use on average 9,415.7 gallons of water for a month. Based on earlier data, the population derivation, so now notice this is a little bit different than what we might encounter in real life. Then we have population derivation, right? Is this 389.6 gallons. So there's our sigma, 389.6 gallons of water used. So now we're going to make a 95% confidence interval, right? So our confidence level, 95%, or as a decimal point, 95, for the average monthly residential water use for all, right, for the population. For that city, okay? So now our goal here is that we're trying to figure out what that mean mu can be between. And the formula, in case we want to use that, we start off with that X bar for our point estimate. Then we're going to add or subtract. Now, because we have the standard deviation for the population, sigma, we're going to see here that same z sub alpha over 2, kind of like our proportions. But now we're going to multiply that by fraction with square root in the denominator. But we're going to have our population derivation sigma in the numerators and our sample size n inside that square root below. Okay. And so we can use that information, right? That same kind of normal distribution to figure out that z cutoff score, like we did with the proportions. But again, on StatCrunch, using that method, you go to the stat menu. Then now we're going to go down to z stats, right? Because we're using z scores, we're going to go to z stats, one sample. And then again, we have the summary of our information here. We'll see a problem in a moment when we have the raw data, okay? But there we go, one sample with summary. And so on our StatCrunch, stat z stats, one sample with summary, okay? Sample mean, right? That value 9,415.7. Standard deviation, 389.6 gallons of water. Our sample size, there was 40 households. We're doing a confidence interval. Again, a lot of times it's 95%, or we could do 99, 90%, 98%, all those different possibilities. We can show our critical value, so highlighting those components, computing, and notice, right, the same critical z-score that we saw with a proportion. Z's there, sample size n, 40. There's our sample mean we typed in. And now we have our lower limit, upper limit, right? That lower bound, upper bound based on that data. Okay. And so as I start to build up with StatCrunch, mu, that population mean, is going to be between, right? That lower limit, 9,294.9639, upper bound, 9,536.4361. So we round here, and now with the mean, we commonly keep the same number of decimal places that we had with our sample data, or in this case, even a population derivation was given, but I'll round the same number of decimal places, one decimal place. So that 6 is going to round that 9 up. And again, that 9 is going to make this become 9,295.0, right? That 6 pushes that 9 up to the 10, if you will. Gallons of water used per month, less than mu. Rounding to one decimal place here, that 3 less the 5, the 4 stay the same. So 9,536.4 gallons of water, right? So at 95% confidence, we were going to estimate that the average number of gallons of water used in this by households in the city, for all households in that city, is between these amounts, right? Gallons of water for that 1 month period, right? With 95% confidence. So now in this next problem, which is, again, a lot more common with the work that we'll see, that we have, okay, this time that market researcher wants to find a 95% or 99% confidence interval. So my confidence level here, 99% or 0.99. For the mean, right, that mu, the number of visitors to a theme park, right, how much they spend per person per day. So the amount of money that these visitors spend each day. All right, so the researcher surveyed 50 theme park guests. So there's our N, 50 guests, and found that the mean amount spent for that sample was $76. So there's our X bar, $76. Right, whole dollars there, no change. She knows that the standard deviation of the amount spent per person per day by all visitors in the park. Well, here, let me swap this out because it should be, right, for that sample. Let's see that part, sorry. The sample, I should clean this up. The sample of visitors, okay? Let's say here this S is $11. There we go, better. Okay. By the sample visitors, $11. We typically don't have that population, okay? And so you'll see kind of like this for the standard deviation for the sample, it'll kind of read like so. And we want to construct that 99% confidence interval for that true population mean, mu, of those amounts spent per day, right? So now we're going to look at this value for mu and have it between our bounds. We're going to start off with our X bar. Then we're going to add and subtract. This time, we're going to start to see this T sub alpha over 2. Let me put it in green, make that stand out. T distribution. And now we're going to have our sample standard deviation S over the square root, right? So it looks very similar, of course, to what we did with our normal distribution. But now we have to be careful. If we only have a sample standard deviation, then we're using the T distribution, right? So on StatCrunch, pull this one down, we don't need to see that. Now we're going to do T-stats, okay? So let me make that note here on StatCrunch. When we only have the sample standard deviation, we're going to go to the stat menu. Then we're going to go down to T-stats. We have one sample that we're working on with a sum. So if you start to put that in, very similar, just keep track of which distribution we're using. So now our sample mean, you saw it, that's $76 that they're spending. The sample standard deviation, $11. The sample size, those 50 guests. We'll make it a confidence interval. Now we're doing 99% confidence. Show that critical value. Computing. And so now we get this critical t-score. Notice that, right? So this is my t sub alpha over 2. We can see there. Okay. So on that StatCrunch, using the same information, our t sub alpha over 2, that long decimal 2.679952. And what we commonly see with the t distribution, we round it to 3 decimal places. So this would have been 2.6. This 9 rounds up, so we're going to get 2.80 if we were to use that with a formula. Okay. But on StatCrunch, thankfully, inputting that information for our lower bound, our lower limit, we're getting here, that's 71.830973. Upper limit, upper bound, 80.1690269027. Since we're talking about this amount of money they're spending, and my sample data was whole dollars, I'll round to a whole number here as well. That 8 rounds this up, so we're going to estimate that they spend between $72 per day and now 1 lets us the same and $80 per day. Okay. So with 99% confidence, we're identifying that these customers, these guests at this theme park, on average spend $72 to $80 per person. Right, that's not full day, but per person they're spending that amount, right, for food, for activities, or for kind of souvenirs, whatever it might be. We're estimating that they're spending between these amounts per day at that theme park. Okay. So now that's when we are kind of given this summary of our data, keeping track here, right, with a sample standard deviation. We're using the t-distribution, population standard deviation, which is pretty rare. We're using the normal z-distribution. So now another option, which again, with projects you might do for work or for school, so on, in your own research, you might be given or only be working with raw data as a sample. Okay, so the length in minutes of a random selection of popular children's animated films are listed below, right? So this is just a sample. We know there's a lot more movies out there. Estimate the true mean length of all children's animated films with 98% confidence, right? So in this case, here, our confidence level, 98%, or its decimal 0.98. But now, in this problem, we have raw data. And so we could calculate the mean for that sample, the standard deviation for that sample, okay? Don't forget that this is for the sample. Similar to what we did with our summary stats before, we can calculate the mean, the sample mean X bar, the sample standard deviation S, and then go into our work in calculating that with StatCrunch in the formulas later, okay? But on StatCrunch, if we have that raw data, what we can do, right? First up, input that data into a column, right? So on our StatCrunch over here, let me close this one down. Whatever column you want to use, I can start to type in 93 minutes, 83 minutes, 76, 90, 92, make sure I type that right. 77, 81, 78, 100, 78, 76, and then 75. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 data values there. And then once I have that data into a column on StatCrunch, now we go to that stat menu. Since it's just sample, it doesn't say anything about having a population segregational. We're going to go to T-stats. We only have one sample we're working on, but now we have data. So we're going to say with data. If we had done the calculations earlier to get X bar, to get S, then we go with sample. But now, since we have that raw data, we'll let it do that work. The stats here, one sample with data. Now we select the column, variable 1, or if you want to label that times, right? We're doing a confidence interval, 98%. Okay. I'm not worried about making any graphs, but I'll make sure to show that critical value. I'm not doing any of the graphing there. I'll compute. And now, just like before, just like when we had that sample data, notice it's giving you this long value, but we have all that information, the degree of freedom, 10, right? And minus 1, if our value for n is 11 data values, our degree of freedom, n minus 1, right? 11 minus 1, our degree of freedom, 10. Is giving you that critical value. But now we're jumping straight into it for that mean, that average length of these films from StatCrunch, the lower limit, 75.562834. Upper bound, upper limit, 89.709893. Now that we have raw data, kind of like when we're calculating the sample mean, sample derivation from that raw data, we'll keep one more. So when we have raw data, I keep one more decimal place. Then the raw data, those are all whole numbers, or around one extra. So I get between 75.6, right, minutes for that film, less than mu, less than 89.0, less than 767 minutes. And so for our summary, right, with 98% confidence, we're estimating that for all children's animated films, that they're going to be between 75.6 minutes and 89.7 minutes. Okay, so estimate what that population value would be if we're able to calculate based on that sample. All right, and so we'll post this information, give you the opportunity to practice with StatCrunch, evaluating. And again, it's up to you whether you want to use those formulas or truthfully with our tools that we have available. It's probably much easier to just plug in our values, that summary or this raw data, and let the calculations go from there. Okay? All right, y'all. So take care. Hopefully this was clear. Any questions, let me know.